Quantum computing is a technological breakthrough that has changed how we process information. Unlike classical computers, which use bits that can only be 0 or 1, quantum computers use qubits. These qubits can exist in a state of superposition, meaning they can be both 0 and 1 at the same time. This difference is not just a small detail, it has huge implications. It allows quantum computers to perform calculations at speeds that are incomprehensible to classical systems. For example, a complex problem that would take a traditional supercomputer 10 trillion years to solve can be completed by a quantum computer in just a few minutes. One of the most exciting advancements in this field is Google's Willow chip. This revolutionary processor has pushed the limits of computation to new heights. Scientists and researchers are now exploring not just the limits of technology but also the very nature of reality itself. The task that Willow accomplished involved solving a problem related to random distribution benchmarks. This task requires navigating incredibly complex and entangled quantum patterns. Classical computers would find such a task nearly impossible, needing an unfathomable amount of time. Yet Willow completed it in under 5 minutes, showcasing a level of efficiency never seen before. This achievement marks a significant milestone in what scientists call quantum supremacy. This term refers to the point where a quantum computer outperforms even the most advanced classical systems. Back in 2019, Google claimed to have achieved this milestone with a 50-qubit chip that solved a problem in 200 seconds. They argued that this problem would take a classical supercomputer 10,000 years to solve. However, IBM challenged this claim, suggesting that the problem could be solved using classical methods in just a few days. Despite this skepticism, the development of Willow, with its 105 qubits, represents a quantum leap forward. Each additional qubit exponentially increases the computational power of a quantum processor. This makes Willow vastly more powerful than its predecessors. What makes Willow's success even more impressive are the advancements in error correction techniques. Quantum systems are notoriously fragile, and even the slightest environmental disturbance can cause computational errors. Google's progress in stabilizing qubits and improving error correction has made Willow not only faster but also more reliable. So what does this mean for the future? While Willow's achievement is largely theoretical, solving the random distribution benchmark does not have immediate practical applications. However, it showcases the transformative potential of quantum computing. In time, machines like Willow could revolutionize fields such as cryptography, drug discovery, material science, and climate modeling. The possibilities are vast, and this milestone offers a tantalizing glimpse of what is to come. But there's another aspect of Willow's achievement that has captured the imagination of scientists and philosophers alike: the possibility of parallel universes. This idea, which sounds like science fiction, is rooted in serious physics, specifically the multiverse hypothesis. Quantum mechanics tells us that particles can exist in multiple states simultaneously, a phenomenon known as superposition. However, when these particles are measured, they appear to collapse into a single state. This is the foundation of the Copenhagen interpretation, the most widely accepted explanation of quantum mechanics. But what if those other states don't actually disappear? Physicist David Deutsch, a pioneer of quantum theory, proposed the many worlds interpretation. This theory suggests that every possible outcome of a quantum event exists in its own parallel universe. For example, if you flip a coin, it might land heads in one universe and tails in another. Scaling this up to a quantum computer like Willow, the hypothesis suggests that when it performs a calculation, it might be exploring different solutions simultaneously across countless parallel universes. The final answer would then emerge in our universe as the product of collaboration across infinite realities. It's a mind-bending concept that, if true, could offer a profound explanation for the seemingly magical speed of quantum computation. Of course, not everyone agrees with the multiverse theory. Many physicists favor the Copenhagen interpretation, which sees quantum states as probabilities that collapse into a single outcome when observed. There is no need to invoke parallel worlds. Whether Willow is tapping into alternate realities or simply exploiting the extraordinary properties of quantum mechanics, its performance is undeniably impressive. Still, skepticism remains. Critics have pointed out that Willow's achievement, while remarkable, involved solving a theoretical problem with no immediate real-world utility. Physicist Sabine Horsenfelder, among others, has likened this to building the fastest race car and testing it on an empty track, exciting but not yet transformative. There's also the issue of scalability. While 105 qubits represent a significant leap forward, practical quantum computing will require millions of qubits working reliably and without errors. Despite these challenges, none of this diminishes the importance of Willow's achievement. Each milestone, however theoretical, brings us closer to a future where quantum computers could solve problems beyond our current comprehension. From faster drug discovery to breakthroughs in material science and ultra-secure encryption, the possibilities are staggering. Willow is a step forward, a testament to the power of human ingenuity and a glimpse of what lies ahead. Quantum computers are still in the early stages of development, but they operate based on principles of quantum mechanics, which govern the behavior of particles at very small scales. One of the most intriguing aspects of quantum mechanics is the idea of superposition, where qubits can exist in multiple states simultaneously, and entanglement, where the states of qubits can become linked. This means that the state of one qubit can affect the state of another, even at a distance. The idea of tapping into parallel universes comes from a concept in quantum mechanics known as the many-worlds interpretation. This suggests that every quantum event can lead to multiple possible outcomes, each occurring in a separate branch of the universe. According to MWI, every time a quantum measurement is made, the universe splits, creating parallel versions of reality where each outcome happens. However, quantum computers themselves don't directly allow us to access parallel universes in the literal sense. They leverage quantum phenomena like superposition and entanglement to perform computations that would be infeasible for classical computers. But they don't imply that we can interact with alternate realities. The idea of parallel universes is more a philosophical or theoretical extension of quantum mechanics rather than something directly achievable with current or foreseeable quantum computing technology. So while the link between quantum mechanics and parallel universes is a fascinating theoretical idea, it doesn't mean that quantum computers allow us to tap into these other realities. Instead, they offer the potential for faster, more complex computation by exploiting quantum states and behaviors. While the direct connection between quantum computing and parallel universes remains speculative, the ability of quantum computers to handle complex calculations involving probabilities and superpositions brings us closer to testing some foundational ideas of quantum mechanics. For example, quantum simulations could allow scientists to model the behavior of systems with multiple possible outcomes, mirroring the behavior that would occur in a multiverse scenario. The advent of powerful quantum computers like Google's quantum chip could enable physicists to run simulations that model quantum events in parallel worlds, potentially revealing new insights into the nature of reality. Moreover, quantum computing has a unique link to the concept of wormholes, another theoretical idea tied to the possibility of accessing parallel universes. Wormholes are hypothetical shortcuts through spacetime that could connect distant parts of the universe or even different universes altogether. In the context of quantum computing, the processing power needed to simulate such complex structures could be a major step toward understanding whether wormholes or similar phenomena could be feasible. Google's quantum chip might one day play a role in simulating these extreme conditions, allowing scientists to test theories about the interconnectedness of different universes. Though we are still far from accessing parallel universes or traveling through wormholes, quantum computing provides a fascinating glimpse into how the complex and often counterintuitive behaviors of quantum mechanics might reveal more about the fabric of our reality. Google's quantum chip and other advancements in quantum computing are offering tools that could aid in exploring these mysterious and fundamental questions. Ultimately, they push the boundaries of science and technology in ways that were previously unimaginable. So, are quantum computers like Willow tapping into parallel worlds, or is their power simply a reflection of advanced probability manipulation? The truth is, we don't know yet. But as we continue to explore the mysteries of quantum mechanics, one thing is certain: the journey will be as fascinating as the discoveries themselves. Subscribe to our channel, and thanks for watching.